Okay, good morning, everyone. I'm going to talk today about work that we have done about combining use of high-performance first principles computations with Monte Carlo, and then more recently with machine learning methods to try to understand and predict the statistical mechanics of materials. And a bit different from what we usually have been discussing here, there's a strong focus on the statistical mechanics. So we want to describe the behavior of a large ensemble of the constituent particles that give rise to macroscopic observables. So ultimately, to connect the microscopic behavior of a material to its macroscopic observed thermodynamics. And as we know, a physical system can be described by its phase space coordinates. So that would be the state of all of the constituent particles, their position, their momentum, what atomic species it is, what is their magnetic moment, and so forth. The dimension of this phase space is huge. So just if you think about a simple gas, monoatomic simple gas like a noble gas, it's actually a 6n-dimensional phase space. So the positions and the momentum of each of the particles in the gas. But in general, the behavior of the system can be understood and is determined by the Hamiltonian of the system, that is the function that maps a point in this high-dimensional phase space into a single real number, namely the energy of the system. So what do we need to understand the statistical mechanics here? At any finite non-zero temperature, or throughout this talk, I might also use the inverse temperature and denote it by beta, which is 1 over K Boltzmann times T. A system is in a particular microstate with a probability that is given by this Boltzmann distribution here. So it's a probability that depends on the temperature and the energy of this state. The observables of a system are then can then be measured as an average over this probability density. So you have the instantaneous value of any observable here labeled A at a given phase space point, and then averaged over the whole phase space weighted with this probability density. And the evaluation of this integral, which obviously is far too complicated and high-dimensional to evaluate for any real system with straightforward method, is actually one of the original applications of the Metropolis algorithm. So to perform some statistical sampling of this phase space to give an estimation of this integral. So what we want to do here is to look at the statistical mechanics of materials from first principles. So traditionally, if you apply these Monte Carlo sampling methods, you use a simple model where the energy is very fast and easy to evaluate, because you still need many, many hundreds of thousands or millions of evaluations of this Hamiltonian to get good statistics over a wide energy and temperature range. So what we want to do is combine these statistical mechanics methods with first principles, and in particular density functional theory calculations. In the other talks, we have looked at, in particular, the use of multiple scattering methods to solve the underlying Cohen-Sham equations to get the energy of the system. So here, the evaluation of the energy requires usually many CPU hours to evaluate just a single energy point, versus the milliseconds or so that it would require for a simple model like a Eisenbach model, or even a classical force field model. So any reduction in the number of energy calculations will, first principles energy evaluations will save a significant amount of computational resources, and actually might translate this sort of desire of doing first principle statistical mechanics of materials from a dream to a reality. So, and an important part that we'll explore therefore is to build material-specific surrogate models from these first principles results to connect to the necessary evaluations of the Hamiltonian in the Monte Carlo simulations. So to give some motivation, I'll show you a few previous examples. So one is here, we wanted to look at what is the effect of the movements of the atom, of the lattice vibrations on the thermodynamics of the statistical mechanics of a magnet. And in particular, we looked here at iron, BCC iron, and how it transforms from ferromagnetic, goes through the current temperature, so from ferromagnetic to losing its overall magnetic order. At the same time, of course, the atoms are moving around, vibrating. So this will affect the interactions of the magnetic interactions of the moments on the individual sides. So to do this, we perform first principles calculation here using LSMS, with for many atom displacements and varying the atomic order to determine the magnetic exchange interaction, the Jij, between all the different atom pairs in the system. And that are, again, a few, some thousand, a few thousand LSMS first principles calculation, denoted on the left side with the black squares. So after quite a lot of effort, Junshi Yin at that time managed to come up with a model presented down there that parameterizes the exchange interaction in terms of various inputs that are related to what's used in EAM models for atomic movements. So the distance between the sides are the EAM density, average EAM densities at the sides and at the midpoints, and sort of the local distortion of the area, that is how much free space is available, accounting for the shape and the distortion of the delta BCC lattice. And using this, we can very nicely reproduce the specific heat in the system using a Monte Carlo simulation. And you see in the cross-hatched area, identify the contribution of the coupling between the lattice vibrations and the magnetism in the system that is not captured by a model that only considers sort of the average, does not consider this coupling. And again, it very nicely reproduces the experimental value, which is the black squares here. Please note that at very low temperatures, you'll see that our model goes to a constant constant specific heat because it is a classical model, classical simulation. So we do not have the quantum mechanically correct behavior of the specific heat going to zero.
So Marcus, can you explain? Can you mention? Is there an easy, intuitive way to understand this contribution to lattice vibrations to make the specific heat peak so much larger? Is there a heuristic argument to tell us why is that happening?
So it mainly comes from the fact that by this coupling, you increase the amount of fluctuations in the system. So if you, because you can have a transfer, basically angular momentum transfer between the momentum and angular momentum transfer between the different subsystems more easily. So you increase the overall fluctuations, which is basically a measure for the size of the specific heat there. If you do not have the coupling, you have separate, basically separate subsystems that are not talking to each other as effectively.
I see. Very, very nice. I did not know about this. It's very impressive. Thank you.
So, and then another example here is to look at order disorder transitions in alloys. And an example here is the copper zinc system, and is particularly the 50% copper, 50% zinc BCC system, where we have a transition from a ordered to a disordered phase, so beta prime to beta here at around 500 Celsius. So we want to see if we can describe this completely from first principles, and to do this we used our Wang-Landau, the Wang-Landau sampling method, and considered random placement of these atoms on the different lattice sides, moving them around, calculating the total energy of the system from with a large LSMS supercell, and accumulating the Wang-Landau density of state, which is essentially the microcanonical entropy of the system. Doing this, and for fairly small system of just 250 sides, we consider these Monte Carlo moves that swap the occupation of randomly selected sides, and then fully self-consistently calculate the energy for each of these calculations. And again, we find the phase transition here around 120 Kelvin above the experimental value. Again, we have to note, because of limited computing resources and complications of displacing in the LSMS code at that time, this calculation do not include the lattice vibrations here. So just the configurational entropy basically that contributes. But we nicely are able to identify phase transition, and especially the short range order, if considered as distance from the phase transition, very nicely agrees with experimental values. So the problem here is, if we wanted to extend this, it turns out this is a really expensive and heroic calculation, even on the large supercomputers that we have available here. So to illustrate this, the picture on the left basically shows the movement of the Monte Carlo walkers as function of the Monte Carlo time, so the number of moves. And each pixel in this plot here is basically a fully self-consistent DFT calculation. So in total, to get the results we had to perform about over a million of DFT calculations. And ultimately, there were about 600,000 accepted moves and 60% rejected moves. So,
do you know why are there these big like stripes or white blobs, these structures in this left diagram?
oh, that is basically from, there are multiple walkers in the simulation. So, each of these stripes is basically the region of one walker that explores a region around it. As you progress, and you do see this, it should get evened out as it spreads over there. Basically, as long as there are these very strong stripes visible, that also tells you that there is still some correlation in the walker, that so the Monte Carlo is not converged yet. So ultimately it should spread out, and the structure should vanish mostly. I mean, there's always local fluctuations that could give you some pattern, but sort of this whole stripes clearly tell you that there are still some correlation. And also we did not drive the simulation to really converge it for all energies, for all temperatures. And you see this in this kink in the specific heat So basically, all the very low energy states are not yet properly explored. That's why the very low temperature behaviors is not quite captured. Of course, this was a very heroic calculation. So how are we going to go about doing something more scalable and more readily available? And I mean, it has been done quite a lot in the past, and is still being done quite a lot also by other groups, as using things like cluster expansion, where you take an ansatz where you say, oh, the total energy of the system can be written in terms of contributions from all sort of possible clusters in the system. Now, this then has to be fitted to first principles calculations. And the question is, oh, how do you perform this fitting without having overfitting and having at the same time a good representation of the first principles of the model. So here we were looking at iron cobalt system, and again the ordering transition in the system, and because of the complexity of this model and what we have available in first principles calculation, it's important to identify what is actually the model that is supported by the underlying first principles data, and so both what is the range of the interaction to consider and the size of the clusters to consider. Doing this analysis, we ultimately find transition temperature to be somewhere in the range of 840 to 930 Kelvin, which is consistent with the experimentally suggested transition just below 1000 Kelvin for this system. So these were sort of the past approaches here. There is this very expensive, completely first principles approach. There's the very tedious manual building of a model that we've seen. And then there is this cluster expansion approach that has quite a lot of what in the language of machine learning would be called hyperparameter optimization. So finding how many terms to keep and what range of interactions to include. So our goal here again is to accelerate the Monte Carlo sampling. Where does the cost of computation come from? They're basically the calculation of the changes in energy. So this is the cost of the DFT calculation itself, but then there is also the probability with which you use generated proposed move. So the acceptance probability of a move, or the acceptance rate of a move. And of course, we want to minimize the total time, which is a sum of all the times here. So how do we perform a Monte Carlo simulation? We first generate a new configuration called X star here from a given configuration we're at the moment. And we generate this from some probability distribution on the phase space, calculate the change in energy between these two configurations, and accept it with a probability that depends on these energy difference. And then we calculate and accumulate the physical observables, and then we repeat this step until we have the desired accuracy of the model. So this is sort of the standard Metropolis Monte Carlo. I'm not going to describe the Wang-Landau method here, where we basically have an algorithm to calculate the microcanonical entropy instead. So we want to minimize the number of the expensive evaluations of the model. So to build machine learning models, we could take two approaches. Either we predict, we build a regression model that predicts the probability density distribution P of X. And that essentially, because this probability is just the exponential of the energy, it amounts to predicting the energy of a configuration. And another approach could be, can we actually model the acceptance probability directly as a classifier model to directly generate the Monte Carlo moves. So there are some ideas of generating, of building generative models that really generate new states directly. That is something I'm not going to go into more details here. It has been tried, but we found that actually learning a model for that is about as expensive as performing the whole Monte Carlo simulation in the first place. So we want to learn basically a model for the energy. And there are various approaches. And in general, what we're looking at here is supervised learning. So we have, from our first principles calculation, basically labeled data, which gives us the phase space configuration and the energy as a label. So we want to predict the total energy associated with a given lattice configuration for an alloy system example here. So we start out, generate multiple lattice configurations, and we calculate the energy of these with our DFT calculations. And then we use these to train a model that is a neural network, for example, that represents the energy of an arbitrary, newly chosen configuration. Now, there are a number of challenges, though. As always in regression, and especially in regression where you have a model with many parameters, and neural networks have many internal parameters, basically the weights on each of the nodes, there is a serious risk of overfitting, as the ratio of the first principles data we have to the internal parameters of the model can be very unfavorable. And also numerical problems, as the training of a neural network, and it's been, shown in the past that neural networks can have a very complicated surface of minima that we again could get stuck in a local minimum optimization minimum that is not representative of the underlying physics. So the idea.
So Marcus, just one question here. You said there are local minima of the energy. This is true, but it's not necessarily mean that there's no consequence in the physics. You know, you can get stuck in a metastable.
What I mean is the local minima of the a training function of the energy, not the energy surface of the system, but the energy surface of the loss function.
I see. I see. So is this known to happen often? Because this would be a real problem.
Actually, that is also what underlies things like attacks on generative on models where you can build sort of fake pictures of dogs that are recognized as cats.
Really? I see. I didn't know that. That's very interesting.
Scary. There are these well-known examples where you train neural networks to distinguish between different pictures, and then you can take this and make just a few changes, a few pixels in the picture. For a human, it still is very clear what it is, but a neural network will completely go down the wrong track.
Wow. Oh, that's good to know. That's really good. Yeah, thank you. Very good to know.
So the idea here is to provide additional information, and ultimately we want to have a model that predicts the energy. But the first principles, the DFT calculation, actually provides much more data, like the charge density, like the magnetization density of the system. So we have additional physical constraints that we know the system has has to fulfill. So we can use this additional information basically by, instead of having a neural network that just predicts one of these quantities or all of these quantities separately, try to build a model that predicts all of them. Ultimately, we are really only interested in the energy, but by training the model so that it predicts all of them concurrently, which is sort of this joint training, which is actually multitask training, called multitasking training. We can significantly improve in the prediction and the generalizability of the energy prediction. So essentially what it amounts to, in addition to minimizing the internal parameters W of the neural network just to predict the energy, we introduce this additional essentially regularization parameter that also predicts the additional physical constraints on the system. And then going forward, we now want to look at other ways of sort of combining some of these ideas now with modeling of transitions in high entropy alloys. What we've done here is to make an ansatz, again, where we consider some model for these high entropy alloys, where sigma is the site occupation by different species interactions, and so this idea here is sort of still in the spirit of the cluster expansion, or actually just the pair interaction model here, and going out to multiple scale shells. So how do we determine what information is actually supported by the training data we have? And here we start out by a set of initial configurations, train a model using this data set, look at the Bayesian information criterion to select the optimum number of shells that is actually supported by this model, and then perform the Monte Carlo simulation. And these simulations then will explore new phase spaces that were not necessarily covered by our training data set. So we can enrich the training data set by performing, again, the DFT calculation for a selection of this new regions of phase space that get discovered, and retrain the model until this whole cycle reaches self-consistency. That is, the model becomes stable and the statistical mechanics predictions become stable. Again, the idea is for our energy model is sort of also inspired by the LSMS approach, where we have these local interaction zones. So we break up the systems into contribution from each of these local sites, and have an ansatz that takes the local contributions to the observables, to the observed energy. Now, it turns out that it is very important for us here to train not only on simulations from one single simulation size, but from DFT calculations on different size cells. That actually helps us to reduce spurious small supercell periodicity errors, and helps in the generalizability of the model. In addition to the pair interaction model, we also apply the same idea to using a neural network, where we basically have a one-hot encoding of the different atomic species on each of the lattice sites within this local interaction zone, multiple number of hidden layers, and finally getting this local energy contribution. Now, for simplicity, I don't show the additional constraints that can be built into this model ultimately, but that's also still work in progress. For these refractory alloy models we've looked at in this work, it turns out that actually this linear pair interaction models gives somewhat better model prediction, and that is mainly due to with a much smaller variation. So this is mainly due to the fact also that the neural network has many more parameters, so there is significantly larger data sets needed to train them sufficiently without, again, the risk of overfitting. Again, that is supported here. So just using now this pair interaction model approach, we demonstrate a workflow that can automate the combination of first principles, machine learning, and statistical mechanics. So we start out by, again, this whatever model ansatz we choose, train it on some initial randomly selected set of data, perform these Monte Carlo simulation that will explore new regions of phase space, here identified by these orange points. So in this case, especially sort of explore some new additional low-lying energies that were not really covered in our original training set, retrain the model based on those, and yeah. So you see that we then go from some significantly reduce the original error in the training set to a much smaller one that then allows us to identify order-disorder transition in these materials, where we go from some high temperature disordered phase to the emergence of partial order to a fully phase separation into two binary systems in this. And that's also then supported in, if you look at the specific heat, and especially you can identify at the lower temperature the different ordering temperatures now of these binary phases. As you see here in this plot, in this graphic on the left, that the molybdenum tantalum phase is already basically completely ordered, whereas the niobium tungsten phase has still a significant amount of disorder. And also we can measure, obviously, the short-range order in these systems. So hope that I've been able to show you here that we can provide a synergy of machine learning and high performance computing to generate first principles training data to build a surrogate model for the statistical mechanics of materials within Monte Carlo simulations. It's very important here to be able to actively refine a model with new data as the simulation progresses. So ultimately that should lead to experimentally verifiable predictions of material-specific finite temperature behavior in complex materials like the high entropy alloys that I've just showed you. So this really is enabled by this tight coupling of these three approaches: first principles calculations, machine learning, and Monte Carlo. Here are a number of the publications of the work that I've presented here, and people who worked on this. Finally, I want to thank the funding agencies, and happy to entertain any questions you might have. Thank you.
Thank you. That's a very nice talk. Let me stop the recording and you guys can discuss.